Hello, welcome back to the bootcamp. Then we move on to the fourth math eco topic, matrices, chapter 6 and 9. But actually, we would only focus on chapter 6 because we would only focus on the basics of matrices and then 2 times 2 matrix. So we will leave 3 times 3 matrix, which is actually chapter 9 for Eco 739, the honors mathematical economics. Some very basic concepts. Actually, it is easier to discuss the basic concepts as well as addition, multiplication, and the 2 times 2 inverse matrices with the study guide actually. But I think for the slides, I have provided many examples, including the economic applications of matrices. So please go through the slides on your own. So now I'm going to focus on the study guide. I think I can enlarge it a bit. Okay, matrices. Okay, we use the capital letter to represent the matrix, and then for each term inside the matrix, we call it element. We rather use small letters. So this is an example. Matrix B, we call it 2 times 2 matrix. The first number stands for the number of rows, and the second number stands for the number of columns. So if I call it 2 times 2 matrix B, then it means there are 2 rows, 2 columns, and then these are the 4 elements. B11 means coming from the first row and first column. B12 would mean the entry or the element located in the first row, second column. And then B21 actually means the element located in the second row, first column. Finally, B22 means the element located in second row, second column. There are 4 special types of matrices. If we have a row factor, it means there's only one row. Okay, this is an example. It is a row factor, but I can also say this is a 1 times 3 matrix. 1 row, 3 columns. So C11 means the element in the first row, first column. C12 means first row, second column. And C13 means first row, third column. But overall, we call it row factor. Column factor, meaning the matrix has only 1 column. So this is an example. It is strictly speaking a 2 times 1 matrix, 2 rows, 1 column. So that explains the element H11 coming from first row, first column, and then H21 coming from second row, first column. And then if all the entries are equal to 0 in the matrix, we call it zero matrix. So this is an example, a 2 times 2 matrix E, and then all the entries are 0. Okay, happy with that? Transpose of matrix, we call it A to AT actually, or A to the power of T. Actually, it's found by replacing the rows by columns. So the first row becomes the first column, second row becomes the second column, and so forth. And I've got 2 examples. Look at the original matrix D, 2 times 3, 2 rows, 3 columns. But now for the transpose of D, the original first row, 2, 4, and 6 now becomes the first column. Similarly, the original second row with the entries 3, 9, and 27 now becomes the second column in the transpose of matrix D. This is another example, the original matrix 3 times 4, 3 rows, 4 columns, and then the transpose, then the original first row with the entries of 1, 3, 5, and 7, the first row of E now becomes first row of the transpose of E, okay, and so forth. Okay, I hope you are still doing fine. Okay, matrix addition is very easy, meaning adding the entries from 2 matrices. But matrix addition is possible only if they have the same orders, meaning the same number of rows and same number of columns. So if we look at A and B, they are both 2 times 2 matrices, same number of rows, 2 rows, and same number of columns, 2 columns. So we can derive matrix C, which is the sum of A and B. So we can add 2 and 5 together, 3 and 7 together, 4 and 8 together, and then 5 and 9 together. And then this is the answer for matrix C. Okay. If you understand matrix addition, then you should also be able to understand matrix subtraction. Just like addition, subtraction is only possible if the 2 matrices have the same number of rows and same number of columns. So this is an example. Both have the same number of rows, D and E, 2 rows, and both have the same number of columns, 2 rows. Then I can derive matrix F, which is D minus E. So that explains 9 minus 7 here, that gives you 2. 10 minus 3 here, that gives you 7, and so forth. Okay. Oh, one thing I need to point out, it is possible to have a negative answer in an element of a matrix. Okay. Scalar multiplication means each term or each element or each entry in the matrix is multiplied by a constant k. So this is an example. Original matrix G, but now each entry or each term is multiplied by a constant 2. So H, which is equal to the new matrix H, which is equal to 2 times G would be, so 5 times 2, 10 times 2, 15 times 2, and so forth. Then this is the answer for matrix H. Okay. Matrix multiplication is only possible, so it's A and B. A has m number of rows, s number of columns, and then B has s number of rows, n number of columns. So this multiplication, C equals A times B. Now this time we multiply two matrices, so it is different from scalar multiplication. Previously, scalar multiplication only involves one matrix. But now we move on to the multiplication of two matrices. So A times B is only possible if the number of columns in the first matrix, which is S here, is the same as the number of rows in the second matrix. So keep this in mind. I repeat, matrix multiplication is only possible if the number of columns in the first matrix is the same as the number of rows in the second matrix. Okay, then this new matrix C would have how many rows? It will be m rows and then n columns. And the last thing you need to keep in mind is that AB is not necessarily the same as BA. So this is an example from the prescribed textbook. This is the first matrix C, 2 times 3. And this is the second matrix, matrix D, 3 times 4. So clearly the number of the number of columns in the first matrix is equal to the number of rows in the second matrix. And then this new matrix E, which is the product of C and D, would have 2 rows, 4 columns. And then I put the entries here, E11, E12, and so forth. Okay, now we need to derive each entry or each element in the new matrix E. So E11 actually means we are using the information from the first row of the first matrix C and the first column of the second matrix D. This is why you see these terms are highlighted. Then we just have to do the multiplication. 5 times 3 plus 1 times 5 plus 2 times 4. So E11 would be 28. Okay, so this is now the first answer. Okay. Okay. Next one. I'm not going to do all of them. Maybe this one, E13, is derived by using the information from the first row of C and the third column of D. First row of the first matrix and the third row of the second matrix. So it is this one. First row of the first matrix and the third column of the second matrix. Then you see the expansion, 5 times 2 plus 1 times 1 plus 2 times 2. That gives you 15. So that explains this term. Okay. This is actually E. I think there's a typo error on the textbook. This is the matrix E. Okay. And then let's randomly do one more. Let's say this one. E24, how can we derive that? Then it means we need to use the information from the second row of the first matrix and the fourth column from the second matrix. So it means here, second row and then fourth column. Then you see the multiplication or the expansion, 4 times 3 plus 0 times 1 plus 3 times 9. So that's 39. And this is how we derive matrix E. So I repeat, there is a typo error on the prescribed textbook here. It should be E, matrix E, the new matrix E, which is the product of C times D. Okay, so matrix multiplication is not that difficult. So you must always remember, for matrix multiplication to be possible, the number of columns in the first matrix must be the same as the number of rows in the second matrix. Okay. Okay, and then this is a nice question, question 6. Okay, about the weekly sales. Okay, week 1, 2 goods, and then 4 restaurants. So week 1 data, week 2 data. And then we can look at the answers. 1.1, you are asked to show the information as matrix. So this is the week 1 data, matrix A. This is the week 2 data, matrix B. And then 1.2 is easy, matrix addition. Just add the first 2 weeks sales together. I think you should be fine. And then 1.3, which is the subtraction, the week 2 sales minus the week 1 sale. And then 1.4c, which says in the third week, the sales is twice the sales in the second week. And then so this is a scalar multiplication, each term multiplied by 2. 1.5 is easy, just add the first 3 weeks sales together. Okay, so this is quite easy. And then this question is quite interesting, A, B, and C, okay? I'm not going to go through the answers. Let's see if it is really possible to multiply the two matrices together. A and B, I think it is possible because A is a 2 times 2 matrix and B is a 2 times 3 matrix. So AB is possible because the number of columns in the first matrix, A, 2 columns, is the same as the number of rows in the second matrix, also 2. Okay? And then rather it is impossible to derive BA, okay, because the number of columns in matrix B, 3 columns, is not the same as the number of rows in matrix A, which is 2. Okay, and then you can also look at the other answers. It is possible to derive AC and CA. The reason is the number of columns in the first matrix is the same as the number of rows in the second matrix. Okay, and then there is another example here. I think it involves matrix multiplication. It is self-explanatory, so I want you to do chapter 6, question 3 on your own. Okay, the product of two matrices gives you the total cost. I think it ends up as a column vector. Okay, and then profit is total revenue. You are already given the total revenue column vector. Then total revenue minus the total cost column vector you derive in 3.1. Then you can derive the profit, I think, in each store actually. So the profit is greater in the first store. Okay, and then chapter 6, question 4. Okay, and then, yeah, another question involving matrix multiplication. Okay, and same, quite straightforward. Again, then you can work out the total revenue matrix, which ends up as a column vector, and then the total cost matrix, which also ends up as a column vector. Then you can derive the profit, which is total revenue minus total cost. Okay, in the next video, we will look at the last topic. Okay, 2 times 2 matrix, determinants, inverse, and Cramer's rule. Okay, it is the relatively more difficult topic of the matrix topic. Okay, but not that difficult actually.